Hello, my name is Arie van der Hoeven. I'm a product manager for Seagate Technology, and I'm here with our technologist, Curtis Stevens, today to give a talk on HDD multi-channel deployment scenarios in Linux environments. And before we move to the agenda, I'll translate that title. By multi-channel, we mean multi-actuator, and today that generally means dual actuator, which is the products that are in market today. And for deployment scenarios in Linux environments, one thing we're looking at is that the technology is moving broader. So there's a need as dual actuator moves to broader adoption. There's a real need for a stress on how it works well in Linux environments. Let's move to the agenda. So we'll start with making the case. We'll start with a couple marketing slides. That's part of my role for multi-channel and multi-actuator. And then we'll transition to Curtis, who will go through our current status and standards and a lot of details on deploying SATA and single-on SAS in Linux environments. And we'll finish with a call to action. And we have a picture here of a dual actuator drive that's pretty popular. That's from our company, Seagate Technologies. Next slide. So let's make the case for multi-actuator. So if you look at this drawing on the right, which should draw your eye, you can see where we were, starting back at about 10 terabytes, 10 terabyte drive sizes. We were already getting down to about 8 IOPS per terabyte. And for some customers, that was already getting pretty close to their limits for what they needed to deliver for an SLA to their customers. As we move forward towards today, we're getting beyond 15 terabyte drives. We start to see some real friction where really for typical data center non-cold storage loads, we're getting to a critical point where it's very important for us to maintain IOPS per terabyte for each drive. Now, there are some things we can do to avoid that or stave it off as an industry. We can try to improve read latency or IOPS without multi-actuator, without making actual hardware changes to new products. We can short stroke the HDD, in which case you're stranding storage capability. You can simply deploy lower capacity drives, but that means a lot more slots are needed. It also comes at a higher cost per terabyte. You can use caching and SSD tiers and SSD caching to help with IOPS, and that's effective to a point. You can change your queue depths, especially if you care less about latency and more about IOPS or vice versa. And then there's some very useful firmware prioritization tools, such as IO priority is a popular one, and one that we and other companies offer in our firmware. Something like stale timers to make sure that no given IOP is allowed to linger too long before it's retried. And those things can be very effective, and we're certainly very active working with partners to try to stretch IOPS as far as we can, but there are trade-offs and diminishing returns to each. So a very important part of avoiding this IOPS wall, unless you're just talking about cold storage, which is growing, especially as more tape moves to hard drives. But unless we're talking about cold storage, there is something that has to break here as we move, especially as we move beyond 18 and 20 terabyte drives. Next slide. All right, so a lot of folks ask about flash, and that's very slide. They do help a lot. One of the key takeaways here is that generally any front-end cache or tiering is very effective for the first, say, 20% of the data. Adding more cache or performance after 20% is not very effective at improving performance, unless you're able to improve performance at that second tier, that's where dual actuator can come into play. So if you have to add a lot more cache to get much of an impact on overall performance once you go above 20, that just doesn't make sense for most customers. So generally we follow an 80-20 rule here. And if you look at this IDC data that Seagate sponsored, And this is really this isn't our data, this is from IDC, so this is a tell not sell slide. You'll see that in general, flash, although it was growing rapidly as far as percentage numbers, it starts to settle in there, not far different than that 20% ratio that we see moving forward, and that's not going to go away. So you can't just simply lay back and say, okay, well, we're never going to hit this IOPS wall because we'll make the transition to flash and all these fabs will come online. That's I'm a flash guy myself. I love that thinking, but dual actuator and other ways of stretching IOPS and HDDs are going to have to be there, and they're going to be there for quite some time. Next slide. So what's happening today with multi-actuator? Well, today we have dual actuator. Our company, Seagate Technologies, has a drive that's a dual actuator, dual LUN SAS. This is delivering performance today with some very large customers in some very large deployments. It is it's being adopted by what I would call kind of our leading edge innovation partners. Folks that can really take a new technology, examine it, and they have the resources to deploy early in a way that's very cost effective and very advantageous to them. For broader adoption, we see that dual actuator, dual LUN SAS kind of breaks that single LUN to single disk paradigm. And we got really strong feedback a year ago here at this conference, SDC. James Borden, my colleague, and Tim Walker, also our colleagues, spoke, and they were presenting on dual actuator, dual LUN and how that works, and got a lot of feedback that it breaks a lot of the paradigms such as device groups, failure domains. The way a lot of companies deploy storage just doesn't work that well. And so, today we're going to be focusing on SATA and single LUN SAS, because we really see that as the key to broadening adoption throughout the industry, and moving beyond just the select innovation deployments that I was talking about. So that also involves some complexity, and Curtis will be going into that quite a bit during his section. And with that, I'll pass on to Curtis. Thank you.
My name is Curtis Stevens. I'm a technologist working for Seagate Technologies. I work mainly in the cloud and enterprise areas. I represent customer needs to standards as well as Seagate, development to standards. Today, I'll be talking about standardized functionality to support multiple actuators. Before I start, however, I'd like to give a little bit of a history of the disk drive in standards. In the beginning, the drive would just run as a unit, and you'd really want to see those LBAs not go bad. And if too many of them went bad, you'd throw out the drive. In ATA, we invented the device fault bit. And when that turned on, you threw away the device. But things are changing, and the device is exposing more of its internal mechanism to the host so that the large amount of storage that's online can be saved as much as you can. So within the last couple of years, you've seen something called head depop enter into standardization. So if a head goes bad in a drive, you can in fact go find out that instead of the whole device is going bad, just a head is going bad. And so today, you can get a report from the device that says this head is about to go bad, and this is all the LBAs that are underneath that head, and you can choose to go save them. In a 9-platter drive, you actually see that a head going bad is about 8%, which means the other 92% of the media is still available to use. And you can continue to use that device, albeit 8% smaller, for as long as you like. If you want to go replace it 3 months later, because that's when the technician is going off to fix things, you can do that. As we move forward, we're adding actuators now, and the device is actually creating multiple read channels. That's really what we mean by actuators in this case. You saw a picture of what the actuators look like. But what it allows you to do is have two fully independent data streams coming off of a device. So as we move forward, what we've seen is that if something happens to a head, the other actuator is totally untouched, and you should be able to continue to use it. So if you look at the failure domains we're talking about, the first level of failure domain is LBAs going bad, sectors going bad. You have a scratch, you had vibration events, so you rode off track a little bit. And those are fully recoverable. You just write that LBA again. Maybe you get a read error, maybe you don't. Maybe the right drive fixes it for you. The second domain now is heads, and the drive is exposing more of its internal mechanism to the host so that it can continue to use the parts of the drive that is still working very well. Now we're reporting actuators, and the first generation is 2 actuators, but generations will follow with more. And then finally, there's the whole device. So if the motor goes bad, or somehow the firmware gets corrupted, then of course the whole drive goes offline. So moving forward today, we've implemented in standards the very basic function of multiple actuators, which is to say, we've got a range of LBAs associated with one actuator and another range of LBAs associated with a different actuator. This allows you to basically divide the drive in half so that LBA 0 through N are actuator 0, and LBA M through max are actuator 1. And typically, or in the beginning anyway, those 2 actuators will all be the same size. There's plenty of room to expand and add more actuator info to the reporting capability that's been added. The reporting capability in ATA is a new log. The log gives you 512 bytes or 1024 bytes of actuator description information. So today, those 1024 bytes or 1K support up to 29 actuators. There is a header record that takes up a couple of them, so otherwise it would be 31. And there's plenty of room to add more. So if we wanted to add, for instance, some head information that would allow you to match some heads to an actuator, we can do that. But what it does is it allows you to divide the drive in half. And if we had 4 actuators, you could divide it into 4 pieces. If we had 3 actuators, you could divide it into 3 pieces. But there's plenty of room to do other things. But this basic functionality is now coming to SAS. And what we're going to see is a VPD page that looks exactly like the SATA log that's being created. It's designed to be fully compatible with SATA so that if you're in a host environment that's developing and you're off using the SCSI low, mid, and higher layers to send your commands to your device, you've got SCSI commands there, which I'm calling SAS here. And then you're going to issue SATA commands. So the translation of SAS to SATA is being provided. And it's designed to be 100% compatible with the SATA device. There's some standardization in process. So I've given you one. We call that splitting the LBA space into pieces so that you can, in fact, put partitions or device map or virtual devices or whatever you want to do on top of the device. The second capability that's currently in development is to allow a single LBA space and have the actuators accesses be interleaved along a stripe boundary. So the idea is you can set a stripe size. Let's say you pick a megabyte. That's a pretty common size. And so every other megabyte begins on a different actuator. We're planning on the capability being host configurable. Devices will present you with the stripe sizes they support. And then you will be able to pick a configuration that the drive provides that you can use. One of the things, there's two uses for this. One of them being is a drop-in performance boost for SATA. So your IOs, if they are pretty random and they're spread around the media, you know, this should get you, you know, a 1.5x to a 1.8x improvement in your read and write performance. The second thing you can do with it is make it match the RAID. If you are plugging it into a RAID controller, you could set stripe sizes to match the stripes that the RAID provides. And then each time the RAID accesses a stripe, it ends up being, you know, all in the same controller. So your sequential accesses remain sequential and your random accesses can go across the stripes and get the benefit of the multiple actuators. So let's talk about deploying a single unsata or multi-actuator device. So the most simplest method I can give you is we have a basic drive. It reports what its the boundaries for its actuators. And you can actually put a partition on each one of those boundaries. So in this drawing on the right, you see partition 1, which is blue, and partition 2, which is overlaid on the green. And your device sees those as two separate entities. One of the nice things this does is it leaves all the power management controls that underlie those two partitions in place. So that if you want to, for instance, spin down the drive, the mechanisms already exist within the stack for requiring, you know, both partitions to be dismounted before it spins down. So the address space gets split and it looks like two independent devices in this case. It gets two independent file systems. You can put them on however you like. By partitioning it at the boundary, you don't have IOs that are going to cross that boundary. Your operating system, your stack, will naturally break IOs that cross that boundary into two different sets so that we don't have IOs that go across actuator boundaries. One of the issues with crossing actuator boundaries is that the IO gets split up by the device into two, and then the IO can take much longer to process than it normally would. This particular configuration is persistent. So once you put it in place, the kernel will recreate the partitions by default because it'll read the GPT and it will in fact provide the partition information to the layers above. One thing to keep in mind is that in a dual actuator device, the GPT is on both actuators, one at the beginning and one at the end. So if something were to happen and one of these actuators were to go offline, the other partition would still be fully functioning and could still be recovered based on the GPT information on that actuator. Second solution is a device mapper solution. This separates the actuators into two separate devices in the system. You may then lay your file system directly down on that device in kind of a raw mode. Or you may put your file system in another partition table on top of those, depending on what you're doing. So it does split it at the actuator split point one more time. However, this configuration is not stored. This configuration must be repeated every time you bring the device up. This can be done with a script, and you can have it automatically run when you start up. Also in this configuration, the device mapper won't generate read look-aheads for you, but it will pass them down if they come from the layers above. Finally, here's a more complex possibility. In this case, what we've done is we've laid the partitions down on the media so that you get the advantage of having the partitions configure themselves. And then from these two partitions, you can go ahead and create a pair of physical volumes that are then mapped into a striped logical volume and a couple of linear logical volumes. So your striped logical volume is there for performance and could be affected if either partition goes down or either side of the drive goes down. But your linear volumes, where you may store recovery metadata, for instance, one of them will remain active if one side or the other goes down. So in this case, you've got a degree of redundancy. You've got the ability to optimize your IOs with some striping that go across the dual actuators. You get a degree of load balancing going on between the stripe logical volume and the physical volumes below. So this is 1, 2, 3 possibilities, and there are many others. As we start to explore how the actuators participate in the system, we're anticipating that we're going to find more applications. The one that we're presenting here is one where if you have a Arie-coded system, you may be trying to optimize your IOs per terabyte. And so each actuator gives you a little bit more. And this would allow you to then begin going from limitations maybe somewhere between, 15 and 20 terabytes to going up as high as 30 with a pair of actuators. And now you've got more data online. You do have more risk. But as I talked about earlier, if you're using head failure technology, you can actually keep your data online and continue using the device. And in something like an erasure-coded system, this gives you the ability to be fault tolerant if a little bit of the data goes offline. In this case, 8%. And it gives you the ability to detect it and to regenerate it elsewhere if you need to.
All right, thank you, Curtis. We'll go on to the call to action. And first of all, send feedback. We really want to see more folks getting involved with Dual Actuator, with how it works for you. We received a ton of great feedback a year ago, basically saying that, yeah, if you have SAS and you have the ability to do dual run and you don't have a typical scenario with failure domains and lights going off on drives and all the number of paradigms that get broken when you have two runs. Let's see, we realized there was a real need for or more of an urgent need for SATA and single run SAS. Inside your organizations, think about that chart. Those charts we showed you. Those weren't. The data was real, and some of it was even from external. So we are looking at some IOPS challenges, some challenges with latency, and these are challenges that increasing your SSD capacities isn't necessarily going to address. And all the litany of things you can do to stretch IOPS are great, but they aren't going to be the end all be all. Start working with your partners on dual actuator enablement. Really start the conversation if you haven't already. This is coming. If it's not here already for you. And we included Linux in the title here for a reason. We really want to drive this in open source and standards. We're looking for more engagement. We have engagements already. Curtis, for example, is very involved with a number of the standards groups. But this is going to become a real focus for us and for the industry as a whole. So with that, thank you very much. We'll go on to the next slide, Curtis. And please take a moment to rate the session. Your feedback matters to us and it matters to SDC. So with that, thank you very much, and we hope to hear from you.